Welcome to Concordia University Sports Space. Welcome back. Thank you for joining us for today's event, part of the Hope and Agency in Uncertain Times Conference. Batteries for Enabling Renewable Energy. Keynote address by Marc-Antoni Goulet. To help situate you, we are streaming to YouTube live from Force Space. We are located on unceded Indigenous lands in Tiohtià:ke, Montreal. And as you know, here at Force Space, we work with our university community to help mobilize knowledge by co-creating daily activities like this one that help examine research questions and projects that are happening across the university. And just to let you know, we're running this event as a live stream Zoom meeting. So we welcome comments and questions there via the chat. Those of you in the space, just raise your hand. We'll get a mic over to you so that everyone can hear. And with that, it's very much my pleasure to hand it over to a chair, Principal, Loyola College for Diversity and Sustainability, Dr. Jim Grant. Jim, welcome back.
Thank you, Doug. And thank you to Fourth Space for collaborating with us on this incredible conference. Welcome to day 2 of our conference. 4 great events today, kicking off with this keynote address by Dr. Goulet. Thank you also for that territorial acknowledgement. For those of you who are maybe online and not coming to us from Tiohtià:ke, Rebecca may put something in the chat. So this might be a good time to if you don't know whose land you're situated on, this link in the chat will help you find out more about your native land. So thanks very much. Okay, so our first event is the keynote address by Dr. Marc-Antoni Goulet. Dr. Goulet is a assistant professor at Concordia University in the Department of Chemical and Materials Engineering. He's also a brand new member of the Loyola Sustainability Research Center, and we always invite our new members to give a keynote address to the conference. Yay! His current research focuses on a really important thing. It's called batteries. And in particularly, he focused on flow batteries, which are a really promising technology. The problem with batteries is reliable energy, and that's what Marc-Antoni will tell us about today. But he also looks at ways for using electrochemically converted CO2 into better products than CO2. He does that. And he tries to create better electrochemical sensors for chemical analysis. So we're really excited to have him here to start off day 2. Thank you for being here, Dr. Goulet, and take it away. First, I want to thank basically everybody that's involved in this kind of research, that enables this kind of research. So my students, my previous supervisors. What about now? Better? Okay. So first, I'd like to thank all the people involved in this kind of research. So from my students to my previous supervisors, to my group members, previous colleagues, collaborators, but also competitors, right? A lot of the technology that I'll be talking about today was done by other researchers that are not necessarily collaborators of mine, but they've worked really hard to enable these technologies. And so I'm going to go ahead and share my screen. Okay. All right. Is that working well? Okay. All right. Well, thank you very much. And I'll just jump right into it. I do have a lot of slides to go through. For those of you on Zoom, unfortunately, you won't be able to see what I'm going to be pointing at on the slides here, but hopefully it'll be pretty obvious. Okay, so outline of the talk. First, I'll talk about greenhouse gases, renewable energy, then grid electricity storage technologies, flow batteries being kind of my specialty of one of those technologies. And then I'll give you a little insight into how that R&D works. Okay, and basically, I'm assuming that everybody here is roughly on the same page, roughly interested in sustainability, and therefore I don't need to tell you about global warming, but I do think that we all work in different areas of sustainability, so not everybody is up to speed on a particular area of it. And so this intro is basically just to give you an idea of where we're at
in terms of greenhouse gas emissions. So here's basically, as you can see, the total greenhouse gas emissions. So it's not relative, it's just total. So obviously we have clear hotspots in the US and China, and now upcoming India. Africa is still not an issue, just because they don't have heavy industry, they don't use CO2 emitting technologies very much. But what's the actual historical trend? So here's the hope for the theme of the conference, is that it is slowing down in terms of total emissions of greenhouse gas emissions. So this is not just CO2, but methane and other kind of global warming gases. And so this is kind of measured in CO2 equivalents. So they have a metric to kind of compare methane, which is more absorbs more heat, but lasts less long in the atmosphere, whereas CO2 can last hundreds of years in the atmosphere, but absorbs a certain amount of heat. So it's good news. Things are slowing down, especially because of the pandemic. We had a little dip there. Hopefully, this doesn't keep going up afterwards, right? Hopefully, we can maintain this and start decreasing it to reach either the Paris Agreement or even better outcomes. So per capita, let's look at kind of who's to blame for these greenhouse gas emissions. So this is not total, but this is per capita. And so obviously the United States, and this is just a few sample countries here, but the idea is that overall the United States was a big emitter per capita, but that is coming down pretty quickly, whereas other countries like Iran or China are actually going up per capita because their economies are developing with heavy manufacturing and energy intensive processes. So in general, however, the world line here, the purple line, is leveling off, and that's related to that maximum output of greenhouse gases. So overall, we are slowing down per capita and slowing down in general. So that's the good news. And when I say agency, another theme of the conference is that, well, if we talk about per capita, that means that every person counts, right? Every person contributes to these greenhouse gas emissions. So we can do something on an individual level to reduce our emissions. How do Canadians compare? Well, we're actually the second worst country in the world for per capita emissions. And I'm not taking this from some arbitrary website. This is actually from the Canadian environmental website, canada.ca. And so we fully admit that we are the worst in 2020, just behind Saudi Arabia. And the United States is pretty close behind, and then Russia, etc. And so this graph on the left just shows that 2005 to 2020 per capita emissions worldwide haven't changed too much, and that was related to that leveling off that I showed before. Okay, so basically, bad news for us is that we have a lot of per capita emissions. This is where our source of Canadian greenhouse gas emissions come from. So it was 15% in 1990, down to 10% in 2014 for electricity generation. So not a big amount of greenhouse gases come from that sector, but the oil and gas sector, which is the production of those tar sands, the production of those oil, those natural gases, and the oil that we sell, mostly sell 44%, I think, to other countries, actually emits greenhouse gases. Then you have, heavy industry obviously needs energy. Agriculture also produces a lot of methane, and that is a greenhouse gas. Waste as well, the decomposition of waste will produce greenhouse gases, etc. So this is kind of, if we do want to, solve the issue, we have to think about all of these different sources of greenhouse gases. All right, again, pointing a little more closely, who is to blame here? Well, those tar sands projects, all of that oil and gas industry happens in Alberta. And in addition, Alberta doesn't have that high of a population. So this is actually total amounts of megatons of CO2. So not necessarily all greenhouse gases, but CO2 at least. Again, coming from the Canadian source website. the idea is that the population of Alberta is less than 4 times that of Ontario. So they have almost 8 times per capita emissions than Ontario, which is kind of one of the worst on this graph. Okay, so if we want to focus more, obviously we need to focus more in Alberta. I think everybody here already knows that. All right, so a little bit of good news is that the economic constraints, the way that I see this graph is that the economic constraints are relaxing a little bit, right? We all have economic pressures in our lives, whether we run a company or work for a company or are just trying to feed our families. In the end, we have to make these economic choices. And it turns out that maybe 20 years ago, it was harder to make the environmental choice. Now it's becoming easier in a sense, right? Because renewable energy is getting cheaper. There's alternatives coming out. There's also other things we can do. Our economies are evolving to move away from CO2 intensive processes. So this graph is a kind of CO2 intensivity of our production. So basically this is kilograms of CO2 per US dollars of GDP. So meaning that our country or these countries are productive, but this is the amount of CO2 that it costs them to be productive. Now, it's not necessarily directly related, but somehow it is relatively correlated, as you can see from these graphs, and that number is coming down for all of these countries. So the idea is that they need less and less CO2 to emit less and less CO2 to actually produce some productive value in the economy. Now, the bad news is Canada is improving the slowest, right? We have the slowest rate of improvement on this. So the hope here is that generally these numbers are coming down, which is good for modern economies, for developed economies. But the agency is that Canada has the most room for improvement, okay? All right, so that was greenhouse gases. So renewable energy. To tackle those different sectors, we have renewable energy that can address those greenhouse gas emitting sources. So obviously, renewable energy is not meant to reduce agricultural greenhouse gases, which comes from methane and decomposition. There's nothing we can do there. But for renewable energy, it's to address the oil and gas industry, manufacturing, household electricity, etc., and transportation, which is a very big one. All right, so again, the historical trend is positive. So this is the share of primary energy consumption from renewable sources. So the idea is that, Canada has always had a pretty large share of all of our energy use, whether it's transportation, electricity, that comes from renewable sources because of hydroelectricity. So we're just lucky as a baseline. And because we're lucky, we haven't actually done that much to improve our overall energy mix. Whereas other countries, so the green curve here is the entire world, is improving in terms of the percent of its energy that comes from renewable sources. So these are solar, wind, hydroelectricity. In some cases, biomass can be included, right? Modern biomass, not just burning trees, geothermal, etc. So these other two big economies, China and the United States, are essentially following this world trend. China is actually doing better on a relative scale. So they're moving faster towards renewables. And so there's the good news, that we are overall increasing relative to non-renewables. And so there's a little bit of projection, a lot of people are interested in, how much are things going to increase over time? And so here's some projections, basically some historical data from the last in 5-year increments. So 2005 to 2010, there wasn't that much renewable capacity growth. So that's basically how many gigawatts, so gigawatts is the power, how many gigawatts were installed in the market, essentially. So how many solar panels, how many wind turbines, were installed in 2005, 2010, not that many, less than 500. But then in 2011, 2016, that increased to almost 1,000. And now we're at, roughly 1,500. And we're expecting it to increase by either double or triple, depending on what kind of projections we're running. And so really we want this trend to accelerate as fast as possible to move that relative amount, that relative percent as fast as possible. Okay, so what are the renewable energy sources coming online? So you can see from 1965 to 2022, hydropower has increased pretty steadily, right? It's the easiest, cheapest one. The technology has been around forever. And so really it's just a matter, most of these cases, these new cases are essentially China, which has tapped most of its rivers at this point to increase their power supply. But what is increasing drastically since 2005 is what we call variable renewables. Okay, hydropower is relatively constant, right? You have a reservoir of water and you can essentially let out some water whenever you want. So you can kind of control the dispatch of the energy. Whereas wind and solar are what we call variable in the sense that we don't really control the supply of energy because it depends on the wind, it depends on the sun. Okay, but both of these sources are increasing quite rapidly since 2005. Now, we might think that this is because of a lot of effort from a lot of different people, and I would say that's generally true, but really the real reason why it's increasing so quickly in those last 10 years is cost, unfortunately. So the way we kind of compare apples to apples is that we call it levelized cost of energy by technology. And so the idea is that you pay for an entire system, like an entire power plant that's either made of natural gas resources or a power plant of solar panels or wind turbines and all of the infrastructure that goes into building those. Those projects, those large scale projects, we kind of levelize the cost. We kind of take the entire capital cost, the operating cost, and then divide it by the number of years or the number of kilowatt hours that it delivers to the customers. And that's what we call by net levelized cost. And so here we have 40 cents per kilowatt hour down to 10 cents per kilowatt hour. And so this might sound a little bit familiar to those of you who have actual accounts with Hydro-Quebec and pay your electricity. So the idea is that these costs have come way down for onshore wind, the blue curve here. It was 30 cents a kilowatt hour. Now it's down to less than 5 cents per kilowatt hour, right? But that is when the wind is operating. Okay, and then you have solar as well, photovoltaic, so PV, photovoltaic solar. That cost has come way down real quickly in around 2010, started to come down. And so it's because these technologies have become cheaper because of all the research and development into them, the efforts in making them more manufacturable, lasting longer, higher performance. Those are the real reasons, the real drivers why we have more renewables on the market right now. Okay, and so to get down into the actual numbers here, here's an example of the cost of power generation. Again, we're talking about the levelized cost of electricity that comes from these sources. So as an example, here's the dispatchable technologies. The bad guys are here: coal, combined cycle gas plants, nuclear, right? If you look at this column here, the total levelized cost of electricity that comes from these different sources is relatively high in some cases, but for the combined cycle, the most efficient natural gas plants, it's actually $40 per megawatt hour. Now, this is in 2021 dollars for new resources, so new projects that are coming online in 2027. So these kind of contracts have already been signed, they're already kind of planned, And so the prices are relatively well known. Whereas the variable sources, wind, solar, the idea is that now these costs are comparable or even better than that most efficient fossil fuel energy source. Okay, so really, when you ask someone which one do you want, they're going to say, oh, I want the solar, it's cheaper, right? It's better and cheaper, right? This is the real reason why, that uptick in renewable energy is happening. Okay, and just to be clear, these are real costs. They're not including the tax credits that come with, so we can go even lower and force the market a little bit faster to adopt those technologies if we give those tax credits. All right. Now, unfortunately, in 2040, you would imagine, those curves that I showed look pretty exponential. The costs are coming down, but that is starting to slow down. And in general, let's say for 2040 projections of what those costs are going to look like, natural gas combined cycle is going to kind of go up a little bit because natural gas becomes more expensive, et cetera. Equipment becomes more expensive in the future. However, these costs haven't come down any further. And one of the reasons for that is because just generally technologies don't just get exponentially cheaper forever. The idea is it just generally slows down, but also because the best wind spots, the best solar energy spots are starting to get tapped, and there's kind of diminishing returns. In addition, the market is becoming saturated, right? So I'll explain that next. So overall, just for industry or household, the idea is that the market kind of drives everything. And really the market means that the end user cost of electricity has to stay competitive or relatively stable. Otherwise, people are in an uproar, right? And so the issue with variable renewables, as you would imagine, is that essentially wind, so here is normalized power output in times per hour. So this is roughly 20 days of time. And you can see that wind is highly variable, right? So if you are trying to deliver electricity in a stable fashion to household customers, industrial customers, et cetera, it's a very tough job, and you need to have some kind of regulation of what you can supply. And so that's why variable renewables are challenging from a kind of power plant perspective. So solar has this, an extreme variability of basically no sun during the night, lots of sun during some of the days, some sun during other days. And then you have the actual market demand. So usually people get home from work and they turn on all their appliances, they start cooking, they start washing, and that's when you get this uptick in demand. Whereas this is what we would call base load, right? You have a minimum demand that's at all times, and then you have these kind of peaks in demand. And so you have to satisfy that demand, and it's very difficult to do with these variable sources. Okay, so how do we make that variable source supply that variable demand? You need some kind of storage, right? Electricity, unfortunately, as soon as it's generated, as soon as the sun gets absorbed into that photovoltaic panel, it creates those electrons, and they have to go somewhere, right? You can't just, tell them to wait. And so the idea is that you need to store them somewhere. And so there's different forms of energy storage, but either way, you have, depending on how much storage you need, you're going to be able to depending on how much renewable you have on the market, you're going to need more and more longer and longer duration of storage, right? So if you have an energy grid that has mostly, 90% wind, you're going to need very long-term storage because there's total, weeks without wind, right? So you're going to need 24 hours, 100 hours, 200 hours of energy storage. And so this graph kind of shows that essentially, hourly, you need maybe a couple hours of storage if you have 50% of your energy coming from from those variable renewables. But if you have 100% variable renewables, then you're going to need, those batteries that can store, 100 hours, 200 hours of electricity. All right, so now let's talk about that electricity storage. So again, we're getting a little bit more honed in on a specific application. So greenhouse gases, we have transportation, we have electricity, etc. So now we're talking about that electricity, right? So that segment, that sector, which is generating greenhouse gases. So to address that sector, we need grid electricity storage. All right, again, a Canadian case, just as an example. So even in Canada, where we have plenty of hydroelectricity, it turns out that most of our CO2 equivalent greenhouse gases come from what we call stationary combustion sources, right? So this would be that oil and gas plants, flaring gas, burning the gas for heating homes, etc. Whereas the transportation sector is roughly 30%, and that's just the gas in the car, essentially. So really what I'm talking about here for that grid energy storage is that we can replace basically all of this, or most of it, with renewable electricity if we can essentially put enough storage on the market. So as an overall kind of goal, the idea is that what we want is we want to replace these emission-intensive processes with emissionless technologies. And in order to do that, what we need is the variable renewables plus some kind of form of storage, so batteries. So the equation that matters, the design equation, is that the levelized cost of electricity from the renewables plus the levelized cost of the storage, that amount, if it's less than the levelized cost of the electricity coming from this, then we win, right? Then there's absolutely no reason to be doing this, okay? So getting a little bit more into the nitty-gritty of things. So I talked at a high level, basically about the market, the general market, but then you have actual customers, like who's buying these things and why are they buying these things? Who's actually going to buy the battery? If it's the power plant, they're going to buy it for different reasons, right? So they might do it, they might buy small storage to do frequency regulation, right? So frequency regulation, you get power from your outlet at 60 hertz or 50 hertz, depending on the country. And so it's a kind of oscillating signal of electricity, and they need to maintain that frequency no matter what you plug into it. And so to do that, sometimes they need to kind of shift between energy sources. So that's a kind of a low duration application. Then you have things like system peak shaving. I'll explain that in a second. And then you have things like arbitrage. So these are all kind of different reasons why an industrial or grid operator customer might want to invest in storage, okay? So here's an example, a very easy example. So when I showed the grid demand for electricity, it's variable, right? It goes up and down, but the idea is that there's a certain minimum that you always need. You always need a certain amount of power to power all the things that are happening in society during the least intensive times. And so we call that base load, right? So at the very least, you're going to design whatever power plant you have to be able to deliver that base load, right? But then you have these kind of what they call mid-merit, where there is a kind of mid-merit level of, well, maybe you're going to oversize your power plant to be able to satisfy most of the customers most of the time, right? But then you have these peaks where it's just not worth it to over-design your power plant, right? And I say power plant, it's not a negative term. It could be a wind turbine power plant. It could be a solar panel power plant. The idea is you're not going to want to oversize it too much to meet those those kind of rare moments that you need. So instead, you're going to use a storage to kind of take kind of the excess power that you might get from here and put it here. So that's a fairly easy case. If we go more general, kind of more on an interconnected level, at the end of the day, this is starting to sound like a market, a marketplace of electricity with very interconnected resources, lots of different cities, lots of different players. There's actually a financial market for trading and buying electricity, okay? And so technically, you could, in the future, invest in a big battery, right? And then talk to your grid storage operator, right? Talk to Hydro-Quebec and say, okay, I've got extra energy right now. You need it. I'll sell it to you for this much, right? Or you got cheap electricity right now because you don't have much demand for it, so I'll buy it, right? And so that's called energy arbitrage, right? Where basically people are buying and trading electricity. And so this is it's a very complicated graph that says essentially, depending on the cost of your storage, the cost of your battery, you can essentially break even on that market, depending on how much duration, how much electricity you can store, right? So essentially, you need a battery. If you can only store 1 hour of power, then you need a battery that costs $200 per kilowatt hour or less to be able to actually make a profit on that part, okay? And then these are the same graphs, but with yearly variations. So the idea is that it's going to change over time. In years, it's going to become more difficult some years, less difficult in others, depending on weather, depending on the price of oil and gas, et cetera, et cetera. So these are very kind of interesting things to look at when you get into the nitty-gritty of it. But at the end of the day, what I care about is actually developing the technology to actually enable more renewables, to kind of get down below these blue curves in order to basically say that it is cost effective to be able to have renewables and battery instead of those CO2 emitting sources. Okay, so overall, the kind of good news or the need out there is that we need more grid storage on the market. And so these are kind of the total amount of grid storage assets, right? So basically buying a battery, a pumped hydro storage, different types of technology that can store electricity. These assets have kind of gone up over time, and it's going up quite drastically. And so in terms of energy content or in terms of power, they're both kind of increasing exponentially over time. And that's to address the need, the fact that more renewables are coming onto the market means that we need more storage. Okay, so what are these grid storage technologies? I think I should check the time just to make sure. And so what are these grid storage technologies? So there's a lot. There's a lot of people working in a lot of different areas. This is a very busy graph, but I'll just draw your attention to the right here. So these are the different technologies. So lithium ion, LFP technology, lithium ion NMC. So these are two different types of lithium ion batteries. Lead acid battery, same battery that you have in your car. Vanadium redox flow battery, I'll talk about that more later. A zinc air battery or zinc bromine battery. PSH, so pumped storage hydro. CAES is compressed gas. Gravitational thermal hydrogen, right? So these are different ways that you can store electricity. And so they each have, I'm missing the axis on the bottom, I had to cut it out, but essentially on the right side would be higher cost, left side would be lower cost. So the idea is that these different technologies, some of them are more expensive. For instance, for 1 megawatt at 2 hours of storage, you have essentially this vanadium redox flow battery is the most expensive. whereas the lithium ion LFP technology is the least expensive. So if you're going to buy something to store your electricity for this application, you're going to buy the lithium ion LFP technology. Okay, so that is for a very short amount of time. So if you need your phone for only 2 hours, you might buy that battery. If you need your phone to work for 100 hours, right, you might buy the vanadium redox flow battery. Now that's not realistic. I'll explain why in a minute. But the idea is that as you go up in the amount of energy you need to store, so basically the duration that you need that backup power, you're going to invest in different technologies. Okay, so, and then it's also related to the power of the overall system. So if you're like a small company that just wants your own backup generator, your own backup power, you might be at the megawatt at most scale. But if you're a power plant, or if you're a grid operator trying to supply to an entire city, you're going to be at 100 megawatts or a gigawatt, like these very large scales. And when you go to very large scales, then you have other costs that tend to go down. And so other technologies become favorable. So I'll just draw your attention to some of these trends here. So the idea is that for the smaller systems, 1 megawatt, 10 megawatt, the batteries, especially the lithium ion batteries, they tend to win. At higher durations, the flow batteries start to win as well, right, over the lithium ion batteries. At very large systems, you have these other technologies, the pumped hydro storage, the thermal storage, and the compressed air storage that becomes a lot cheaper than those, okay? All right, so pumped stored hydro. I don't know why they called it like that, but basically they're essentially creating their own hydroelectricity, their own dam, by essentially taking water, pumping it up to a reservoir that is at high altitude, and then that's essentially stored energy, right? Because they can let the water come down and operate turbines. Now, this is one of the cheapest forms of energy, and it's already being used around the world. The problem is you need kind of a lot of water close to high altitude elevation changes. And so it's geographically very limited. Can we do it here in Montreal? No, not even close, right? So the idea is that these kind of resources, or these kind of options are becoming more and more limited. There's less and less of them available. They've already been kind of tapped out, just like most rivers in the world have been tapped for hydroelectricity. All right, compressed air energy storage. It's kind of a similar idea where you're taking air, just normal air, you're compressing it, and you're kind of pumping it down into a salt cavern, right? An empty space in the Earth's crust, right? And so that gives you enough space. You pump it down at high pressure, and then you're storing energy in that compressed gas, which you can let out at a different time to operate a turbine and create electricity. So it's fairly easy, kind of well-known technology. Unfortunately, it is also geographically constrained. You need these kind of special caverns that can accept these gases without losing too much efficiency. All right, so that's another good one, another cheap one, but geographically constrained. All right, thermal energy storage. Same idea here. You're essentially storing energy in a medium. In this case, you're storing it in something that can hold heat for a very long time. So you're essentially going to, you have a, basically, let's say a liquid that you can heat up using your renewable electricity, and then becomes hot. You flow it through a medium that you heat up. In this case, the technology is graphite. So basically pencil leads. Excuse me. And the idea is that that graphite can hold that temperature as long as it's insulated, hold it for a long time, and then essentially you can essentially flow your liquid medium out through that hot temperature and extract that heat later, operate a turbine or a steam engine to create electricity, right? So this is relatively old technology, but again, it's relatively inefficient. And the idea is that it's only economical at very large scale. All right, so I won't dwell on this graph here, but each technology has its own advantages, pros and cons. And so here we have kind of energy density versus power density, right? So you have the pumped storage hydro and the compressed air. They have kind of the lowest density in both cases, but they happen to be the cheapest. Okay, flow batteries, vanadium redox flow batteries, also low power density, but a little higher energy density, etc. Right, and then you have these other technologies like lithium ion that has good power density, high energy density, but the cost can be prohibitive if you need a lot of it. All right, so overall, the idea is that we have some cheap technologies that already exist, but they're geographically constrained or they require very large scales. What we need actually is versatility, adaptability, and really batteries are kind of the most versatile, right? Pretty simple devices, you plug them in directly, electricity is stored, and you can deliver that electricity later by plugging them in the other way. So the idea is that there's a need to reach net zero emissions to kind of increase the amount of battery storage. This is the amount of battery storage for grid electricity. It's increasing, but in order to reach net zero by 2030, it needs to increase that much, right? So we need to really start to ramp up production of inexpensive batteries. All right, there are a lot of people working on this. There's a lot of different battery technologies. Some of these, this is kind of just a website. So some of these are not even batteries, like hydrogen storage, nanotechnology. That's just a general term. But the idea is that there's a lot of different startups working in this space for different types of batteries. So I'm just going to contrast kind of the two major types of batteries for grid storage. So grid storage is not like your phone. It's not like your car. You don't need it to be pretty. You don't need it to be dense. You just need it to be cheap, okay? Cheap and safe and reliable. Those are the things that matter for grid storage, right? So think of a solar power plant, a wind power plant out in the boonies, and then under the solar panels, you just have these big batteries that store the electricity, right? Nobody needs to have them be small or light. Okay, so a traditional battery, right? Whether it's the old school batteries that you had, like the D batteries that you had in your stereo back in the 80s, or the lithium ion batteries we use now, the idea is that you have essentially the energy is stored in the electrode. So it's a solid material. That's why your battery is kind of it's a solid device. It has a lot of different layers of electrode, but the energy itself is stored in a solid electrode, okay? Lithium ion, it's stored, the lithium ions essentially go from one side of the battery to the other. On one side, it tends to be a carbon or lithium metal, and the other side, it tends to be a kind of lithium metal oxide, okay? But lead acid batteries, same idea. The car battery, the energy is stored in the electrodes. To contrast that, a flow battery, the energy is stored in the electrolyte, so the liquid, okay? So a flow battery, essentially, it has electrodes, but these electrodes are inert. And it's basically, they are where the electrolyte will donate or accept its electrons, so its electricity, its energy, where you convert the electrolyte to a charged or discharged form, okay? So the elements or the molecules that are dissolved in the electrolyte are the things that store the energy. So the advantage there is that if you need more energy, you don't need a bigger battery. All you need is more electrolyte. Okay, so that's the big difference between the two types of batteries. In this case, if you need more energy, you just need to buy more batteries, right? To have bigger electrodes, more electrodes, right? So you just double your cost. In this case, if you need more energy, you stick with the same battery, but you just increase the amount of electrolyte. Okay, almost about 2/3 of the way. So flow batteries, when did they start? I will give some credit to Maria Skoulas-Kazakos, the inventor of the vanadium, the all vanadium redox flow battery in 1985, 1986 in Australia. I was very fortunate to do a fellowship in her lab in 2015. And the idea is that vanadium redox flow batteries use vanadium, which rely on the oxidation states of the vanadium element. And so it's nice and colorful here. Vanadium 2+ is purple, vanadium 5+ is yellow. Very nice research to do if you like colors. What is vanadium? Vanadium is just an element of the periodic table. It's one of these transition metal elements. So it's right next to titanium, right next to chromium. And so if you're interested, check out the periodic table for its properties, right? So it's just one of the metal elements out there. Now, like I said, the idea is that a flow battery has an advantage. It's a cost advantage, right? These are not energy dense systems. You wouldn't put them in your car or your phone because you need pumps. The electrolytes can only hold a certain amount of energy. But the idea is that the electrolytes can be very cheap, right? And so if you need more duration of storage, more energy, the cost comes down faster for the vanadium redox flow battery than it does for the lead acid battery. And that's because for the lead acid battery, you need to pay for the electrodes, you need to pay for the electrolytes, the casing, all the components. You have to keep buying more of them. In the vanadium case, you just need to buy more electrolyte. Unfortunately, vanadium is not necessarily cheap enough. So vanadium is used in the steel industry. So there's a lot of competing demands on vanadium. It is also mined material. So there's not necessarily enough of it to address the needs of the amount of storage, the amount of batteries that we need. We don't necessarily have enough vanadium on the planet. So there's a bit of a limitation there. And so that's one of the reasons why startups are having difficulty competing with lithium-ion technology. Is that essentially the price fluctuates, they can't get their materials when they need them, etc. What other options do we have? So we have a whole periodic table of elements. People have tried every combination in the book, right? So these are all kind of different reactions and their potentials. And these are some of the chemistries, the battery chemistries that have been tried. So for example, zinc, cerium, zinc, manganese, titanium manganese, titanium tin, vanadium iron, copper copper. You know, people have tried everything, even neptunium, which is ridiculously rare. So what is going on in flow battery development? So there are startup companies. Some of them are using iron chromium, vanadium, zinc bromine. And so, you know, these are startups that have kind of evolved, kind of been bought out, kind of merged with other companies. And so we do have a bunch of startups still going to try to commercialize these technologies, but it's not a slam dunk. It's not an easy sell. There's a lot of competition in the market. So enter 2013 at Harvard, they decided to investigate organic flow batteries. So the idea is that we want to move away from the elements, right? We want to move away from mining, extracting things from the earth that are scarce, where there's geopolitical conflicts, right? We want to essentially make our own flow battery reactants, and we can. So it turns out that organic molecules, some of them are redox active, meaning that you can change the oxidation state to an oxidized or reduced state, and in that way, it will store electrons. Okay, so here's an example of a flow battery. So here's the battery itself, the electrodes where the reactions happen. These are the tanks of electrolyte, right? And these are the pumps that pump the electrolyte through the battery and out. Okay, so it's a little bit like a car engine. The only thing is that you're not just burning the electrolyte and it disappears. You're just discharging it and putting it back in the reservoir and then recharging it later if you want. So the idea is that this molecule called DHAQ can be oxidized down here or reduced. So you lose kind of one of these oxygen bonds here, and that's related to that oxidation. On the other side of the battery, you have another molecule called ferri or ferrocyanide, which can also change. Here you see the 3 minus and 4 minus. So the oxidation state kind of goes up or down. And so you're just kind of making these oxidation states go up or down on each side of the battery, and that kind of changes essentially the charge state of your battery. Now, again, going back to the idea that the advantage is that the energy, the amount of energy in this battery is just proportional to the size of your tanks, the amount of electrolyte that you have. And so that means the cost of your system is essentially going to approach kind of this cost of the electrolyte alone. As the larger and larger system you have, you just need more electrolyte. So the cost of your overall system is essentially the cost of the electrolyte. And so if these are synthetic electrolytes, then we have a lot of work to do, right, to develop high performance, but also cheap enough electrolytes. All right, so again, we're getting a little bit more technical. A question, yes. Sure.
Are they mixed up on the previous slide, or are those actually 2 tanks on either side?
They are, there's 1 tank on each side. So 1 tank for each electrolyte. So when you pump it in, you will either charge or discharge it. So let's say your battery's at 80% state of charge and you're discharging it. You pump it in and you're going to discharge it, and then it's going to come out maybe at 60% state of charge. But overall, this tank, the state of charge, is going to kind of change gradually over time as you keep sucking the energy out of it. It's the same tank. It's not separate. No. Yeah. Yeah. You just keep the 2 electrolytes separate. You don't want them to mix. Yeah. It's a good question. All right. So again, chemicals, we don't all like chemicals, especially when they're at very large scales. But some of these chemicals are not necessarily that bad. So for instance, anthraquinone, right, the DHAQ I just showed you, is a naturally occurring molecule, depending on what it looks like. In some cases, it can be used as a dye. So alizarin is a type of anthraquinone that comes from madder root, which is a dye that was used to dye your clothes, essentially. They're very brightly colored. And that color is actually related to these kind of electron transfer reactions. Other ones are more, this is methylviologen, not the best. This is actually a pesticide, but the idea is that you can still tweak its functionality to store energy stable. Okay, so just a reminder, the idea is that the advantages of these synthetic reactants is that potentially we can get lower than the price of vanadium or any other elements in the periodic table. Another advantage is that they have rapid kinetics, slow crossover. That's a bit of a tech talk in my field. So the idea is that they have fast reactions, and they also kind of cross that membrane between the 2 sides of the battery very slowly because they tend to be very big molecules. The challenge is the stability. Organic molecules they're susceptible to decomposition, right? They're not elements in the periodic table that are infinitely lasting. They can actually be damaged during operation. And so they will decompose and lose their properties. So that's the biggest challenge, is the stability of these molecules. So I'm going to finish with a little insight into how, I know this is for a general audience, but I'm sure there's at least a few of you that are curious about how we actually do this research. So some of the research, what does this look like? So at the lab scale, right, we're investigating this kind of at a human scale that one person can deal with. So this is an actual flow battery. Those kind of 2 plates in the middle of the flow battery on the bottom, that would be kind of the electrodes, where they have these flow fields right, at the top left. So these little serpentine patterns is where the electrolyte is kind of flowing through the electrode, okay? And then we put the electrode materials on top of that. The electrodes that we use, just carbon, right? Just an inert carbon, because it doesn't react. It is only a surface on which the chemicals react. Okay, and then we separate the two sides with, you can't see it very well here on the right, but a specialized membrane that can allow ions to go back and forth between the two sides, but keep the ones that we want on to be on either side. So we sandwich this together, and that makes the actual battery that we can basically charge and or cycle back and forth. And then these are very small tanks, right? Because at the lab scale, we don't need 20 hours of energy. We just want to investigate what's going on and how do they work. And so we have these nicely colored electrolytes that we will charge and discharge, and they will change color, and we'll be able to make some measurements on those electrolytes, either in the battery or outside the battery later. Perfect. Okay, so that's what the research looks like. What do we look for? All right, getting a little nerdy into the chemistry. The idea is that, you know, batteries, power, electricity, it's all about current and voltage, right? So here on the left, current or current density, so the amount of current that you're getting, and the voltage where those reactions are happening. So the red curve and the blue curve are the two electrolyte species, the two special molecules that are dissolved in the electrolyte. And I should, by the way, mention that my research and most people work on aqueous organic flow batteries. So the idea is that the molecules might be organic molecules, but the solvent is just water, right? So these are not necessarily super harmful. So they might be very acidic or they might be very caustic, but they're not necessarily, you know, harsh solvents, and they're certainly not flammable, right? They will never explode. They will never catch on fire. So the idea is that we will investigate, where does this molecule on the potential scale, where does it react? So it reacts on the left at a very low potential. The other molecule reacts on the right at a relatively high potential. The difference between these two potentials, in this case 1.14 volts, that's going to be the voltage of the battery, right? So if we combine these two chemicals on either side of the battery, we get 1.14 volts, which is not bad for an aqueous battery, okay? That potential will change depending on the pH of the battery. So we have another kind of parameter that we can change to optimize our system. That's all I'm going to say there. This gets a little bit more complicated, but the idea is that the potential of these molecules will depend. So these are kind of the shape of the reaction of it being oxidized and reduced. Okay, it produces a current that's either positive or negative, depending on which way you go in the potential scale. Okay. All I want to show with this slide is that these curves change a lot depending on what is the molecule. Now, these molecules might all look very similar, but they're just slightly different. So for instance, this one has a sulfuric acid or a sulfate group that is 3 carbons away. This one has a sulfate group that is 2 carbons away from the main molecule. And so the chemists that I work with can essentially design or try to produce these different molecules with all these different structures that will tweak the properties of the electrolyte just slightly to get what we want, the performance that we want. Okay, so that's all I want you to take away from this, is that there's a lot of design space. There's a lot of room to design these molecules to have the properties we want. That also means there's a lot of work to do. Going back to the stability issue, the main challenge behind this technology, it's the same idea. So this slide was all about performance. So what is the current at what potential? This slide is all about stability. So back to that molecule that I said is kind of a nasty one. The idea is that the capacity of the battery, so pretend like the capacity, the amount of energy that your phone can store, right? First day, it's fine. After 5 days of using it, you can't seem to get as much energy out of it, right? And after 2 years, the capacity kind of goes down, right? Same idea here. Over time, capacity goes down. If you just add these, what we call functional groups to the molecule, now it's super stable, right? So, and that's because it kind of prevents these kind of little attachments to the molecule, prevent it from decomposing, okay? So I'm going to stop there. That is the kind of research that we do. We essentially are working with chemists to design new molecules to put in these flow batteries and test for essentially performance, stability over time. And then eventually we're going to talk to some process chemists to find out, well, what would it cost to make these electrolytes at a large scale to actually address the market? So I hope you enjoyed the talk. Basically, to summarize a little bit, I'll just read off my slide, but essentially, the good news is that the hope is that the renewables are increasing in number and in relative amount. And then the idea, the problem is now it's energy storage that's becoming the bottleneck, right? It's no longer the price of solar, the price of wind. It's the fact that you can't put 100% on the grid. You need some kind of storage to level out the supply versus demand. And so what we need is new battery technologies or other storage technologies that are cheap enough to kind of allow that, to enable that. And so basically research and development needs to kind of accelerate to keep pace with where we need to go to reach that net zero emissions target. Flow batteries, which is kind of my area, it's a growing research area. It's expanding quite quickly. But there's still, like I said, the design space of all those molecules is huge, right? Millions of molecules that need to be tested. So a lot of work to be done to find kind of the right combo. So I hope that you have taken away a little bit of hope and agency in renewable energy research in particular. And thank you for your attention. I'd welcome any questions you have.
Thank you very much. The hope and agency was fantastic all through the talk. I think we have time for a couple quick questions. Any on, do you want to do Zoom first? Or they're coming. Go ahead, Emma.
For those of you in Zoom, feel free to raise your hand or type your question in the chat and we'll get right to you. Those of you in the space, you can just raise your hand and we'll get you a mic.
So thank you for a great talk. I'm trying to remember my thermodynamics, and what seems to be coming back is that as your battery goes from 80 to 60 to 40 to 20%,
yeah,
are you going to be getting less current? As you're getting closer to an equilibrium between you two?
So that's a deep question, as thermodynamics is, but yes and no. So for flow batteries in particular,
Yes, yeah.
as you discharge your electrolyte, you have less of your reactant to be reacted. So there is kind of a push towards the other direction from a thermodynamic point of view. Also from a what we call a mass transport point of view, you have less of it. You have to get it close to the electrode. It's more difficult to do that. So you do have an efficiency loss. It's not a current loss. So you do get the amount, the current is still there. The energy is in the electrolyte. You can use 100% of it if you want, but to get those last few percent, you need to work harder. So it becomes more and more inefficient to kind of get those last electrons. And so the idea is that generally, just like with your phone battery, you don't want to charge your battery all the way to 100%. You don't want to discharge it all the way to 0%, because technically you're paying more for the electricity that you use near those limits. You kind of want to size your battery so that you only need to go from 20% or 10% to 90%. And that's kind of the same for flow batteries.
So if I can follow up with you mentioned size. I'm trying to visualize these. Are we talking like liters or swimming pools?
Yeah, that's a good
lakes.
Yeah, it's a good question. Basically, it depends on what power you need, right? If you're powering a city, if you're powering Montreal with a flow battery, that flow battery is going to be the size of many football fields. Yeah. in terms of size. Let's pretend tanks that are, I don't know, 10, 20 meters high, like a football field size of
Lights.
tanks. Yeah. Yeah. Small ponds at the very least. Yeah. Yeah. So that's why generally I want to stay away from any kind of non-aqueous solvent type of flow batteries.
Yeah.
I would prefer to work with kind of an aqueous water-based material.
Thank you.
Other questions? Go ahead, Rebecca.
Thank you so much. So interesting. I love hearing about your work. So a couple questions. As a biologist, you were talking about synthetic, but also organic. So we're not talking about, mass producing any kind of plants, or you're producing these molecules in a lab. Is that correct?
Yeah, so you could, like for instance, matter, right? Matter, the matter root used to be processed to extract the alizarin dye, right? That used to be the way they did it in India way back in the day. But the idea is that today it's a lot cheaper to just synthetically produce that alizarin molecule without going through, without processing so much roots and leaves and stuff like that.
Okay. And what is the impact of that production process?
That's a very good question. So, most of the organic molecules out there, whether it's your pharmaceuticals, whether it's, caffeine in sports drinks, whatever organic, whether it's the plastic in your shirts and your, whatever, most of it comes from the oil industry, right? It's actually, it's kind of converted to higher and higher complexity molecules, right? That's an unfortunate reality. Some people, a lot of chemists, for instance, say we should not be burning oil. We need it to make things, right? Because it's the starting material for basically all of the things that we use in our modern day lives. That is the reality right now. There is a branch of chemists, chemical engineers that are working on essentially doing the same from bio-based precursors, right? So the idea is that you can take ethanol that you're taking from, let's say, I'm looking for a word, ethanol coming from the fermentation process, yeah? And then you can kind of tweak that, right? Convert it to other bigger and bigger molecules, right? So organic chemistry, you can go either way. It's just some ways are more difficult than others, right? So some of these molecules, probably they're going to come from oil that's converted to this, that's converted to that, and then you buy that and you convert it to the one that you want for the time being, right? But there's already people looking for alternative routes, alternative pathways to get to that same final product.
Interesting. Thank you. I have another question, but I can.
Sarah.
Oh, I'm just going to add one last detail for that. There is a third route, which I find super interesting. I'm not at all versed in it, but the idea is that kind of combo of modifying nature to use nature to produce what we want, right? So now they're genetically engineering yeast and other kind of microbes to produce molecules, very complex molecules that we want at large scale. So you have these large bioreactors. Basically, that's how we produce, insulin and vaccines and things like that. A lot of them are produced by microbes and things like that, that we just harvest the products that they make. Yeah, so that's a third pathway.
Thanks for a really interesting talk. I'm wondering about, most of your analysis seems like predicated on kind of a mainstream economic model. And I'm wondering, if there's some of the mining for some minerals in particular is particularly damaging. There's, social implications, there's environmental implications that are not taken into account in the just cost model. And I'm wondering how all of this would change if those kinds of impacts were modeled more, and if people are doing that. And
yeah, I mean, that's a great question. At the end of the day, I'm trying to help, right? I don't want to harm more. the fragile planet that we've kind of inherited. And so the idea is that there are people working on that. They usually call it LCA, right? Cradle to cradle analysis, life cycle assessment, right? We have some people in our department who's doing that, not necessarily for flow batteries or other technologies, but there are some people that have.
I guess I was wondering if you've looked at that and how it would shift for flow batteries, the
Versus-
equation for some of these, like, I mean,
Yeah.
lithium ion batteries or.
Yeah.
I know, and okay, and sort of a secondary follow-up question.
Yeah.
I feel like there would be a market for, say, cell phone batteries that are less destructive or less have, you know, fewer socially negative
Yes.
impacts on,
Right.
you know, places where they're being mined for. And is there a way to tap that market with a battery that is maybe a little more costly, but
Yeah.
less has fewer negative impacts?
Yeah, I mean, that's a good question. And unfortunately, the reality behind battery development is that it is a huge undertaking, right? It's going through millions of molecules, one person can do, like I spent 2 years investigating one molecule, right? 2 years full-time as a postdoc investigating what's happening to this one molecule and how do we fix it. So imagine that if you had to scale to produce kind of a new technology, they're just very, very expensive technologies to develop. So there's a big cost in upfront, and the only people that are willing to make those upfront costs are kind of the ones who have the money to spend, and usually those people want to make the most money and therefore want the biggest market, right? Not the niche market, right? They're not going to invest $1 billion to make a battery that 100 people are going to buy, right? That's the unfortunate reality. But academics, we can spend our time kind of investigating those questions, and some people do. Some people do just try to make smaller kind of incremental improvements and kind of test whether there are other kind of better options out there, right? But it's slow. Academic research, and even though there's a lot of people working in it, it's slow, right? And it might be too slow for where we're headed. So, yeah.
Okay, maybe we should call it there. We can continue over coffee
Sure.
with Dr. Goulet. So thank you so much for kicking off our second day. It was a fantastic presentation.
Well, thank you very much for having me.
Rebecca, you want to jump in with
Yeah,
something
I
else?
just want to jump in really, really quickly.
Yep.
I know you're looking for students all the time. And I
Yep.
know we've had this conversation. So I just, while we have an audience here, what kind of students are you looking for? What kind of background are you looking for to work on?
I
This
could
kind of
certainly,
stuff.
chemists are certainly helpful because I don't have a chemistry background myself. I'm physics and electrochemistry. So that's always needed. Just generally, those that are really into research, really into figuring out what's going on, right? Very motivated, self-motivated to actually figure it out. This discipline is very multidisciplinary. You need to be able to take risks and say, oh, I need to learn this, right? I just need to learn it in order to do this thing, and to have kind of the courage and the motivation to accept that, right? They accept the fact that I won't necessarily be able to kind of tell them exactly what to do, what line of code to write, how to make that circuit, how to do that synthetic reaction, right? That they have to have kind of the independence to kind of find out what they need to know, and then go seek out the answer, right? That's what research is.
Be adventurous, courageous, bright.
Yeah.
Physics, chemistry, biochemistry student.
Yeah.
All right. Thank you. Sorry, Jim. That was up. Let me take it. Okay. So I guess that's me. I'm the disembodied voice here because I'm not in front of a camera. Thank you all for coming. today. Thank you, Marc-Antoni. Amazing to hear about your work always. For those of you on Zoom, please join us in just a little less than an hour, right back here, the same way you got here in the room. You're welcome to stay. We have coffee and snacks for everyone. We have the schedule is online, and I can just put my slides up here to see what's coming next. But the next panel is a student panel, a series, kind of a conglomeration of different student project initiatives. Here we go. All right, share the screen for the people who are on Zoom. Okay, so we are running all day today and tomorrow here in the fourth space, so online or in person. Or 10 o'clock, we're already there. But the noon session features a series of our students here at the college and the research center and at Concordia University, graduate students and undergraduate students doing really varied work, from a project on capuchin monkeys to a project on balsa wood and its usefulness for wind turbines and plantation issues. So a lot of really cross-disciplinary work going on the part of our students. At 2:15 this afternoon, we'll be hearing about digital disruptions and how they're changing our environmental systems. This will feature our own professors Damon Matthews in the Geography, Planning and Environment department, and Sabine Bergler, who's in computer science, and Baron Timas, who's in the music department here. So another very cross-disciplinary conversation on digital disruption. So please join us for that. And this afternoon at 3:45, we have a project. We're presenting a project that is very much in process, cross-disciplinary project here, collaboration between professors in the biology, communication studies, political science, and at the college, collaboration with community groups, community conservation groups here in Montreal. So we will have the community groups in the space as well. So we'll be talking about conservation in urban green spaces in Montreal. Tomorrow we have a whole series of events as well, again here at Force-Space, so do join us online or in person. I won't go through the whole list, but a couple of highlights maybe. We have a fantastic group of students who will be talking about bats in the afternoon. We have a keynote address from another one of our new members who's in the education department, Mitchell McLarnon. So do please join us tomorrow morning or at any point tomorrow at Force-Space and online. And then Friday, we will only be at Loyola. Loyola is where the real party is. So there's more food and there's lunch. If you register, it's all free. And we'll have a whole series of student and faculty panels and discussions going on Friday at Loyola. In the meantime, thank you for coming today. I do need to thank all of our sponsors as well as everybody who has physically made this possible. This conference is always presented every year by the Loyola College for Diversity and Sustainability and the Loyola Sustainability Research Center. But we also do have funding from the Office of Research, the School of Community and Public Affairs and First People Studies, the Science College, and the Departments of Biology, Communication Studies, Political Science, and Geography, Planning and Environment. And we are ever grateful for the support and patience and collaboration of the fantastic crew here at Force-Space and the fantastic use of this beautiful space. So thank you, everyone. Please do come back and thank you for coming this morning.
Thank you. Thank you, Rebecca. Thank you for coming in with the Hope and Agency in Uncertain Times conference. Thank you for everyone online and those of you here in the space for all of your questions and contributions. We're going to be closing up the live stream, but just a quick reminder that this conversation is already available on our YouTube channel if you'd like to revisit or share it. So thank you again to Marc-Antoni Goulet for his keynote, and we will see you shortly for all of those wonderful events that Rebecca just explained. So have a great morning, everybody. And